Hello, everyone. I hope you guys are doing well. And remember last time I gave you a reading assignment. You're supposed to read chapter one, and today we will go over a certain section of chapter one, and so I will start introducing five basic concepts. Number one, system. State, property, process, and last one, equilibrium. So those are the five fundamental concepts you must know and remember, and we will use those terms throughout the entire semester. So let's first look at what is a system. System can be defined as a quantity of matters or region. So when people typically describe the quantity of matter or region, we like to draw something called a boundary. And later on, we will go through an example, and you guys will really understand how to draw those boundaries. So typically for boundary, we have two type of boundaries. One is called closed boundary. Another one is open boundary. So what are the differences? So, and for closed boundary, there's a nickname for it. It's called control mass. And the open boundary, we typically call it control volume. And control mass, sometimes we denote as Cm. Control volume, we denote as Cv. So what are the differences? So two things you need to remember for control mass. One is mass cannot pass through the system. And secondly, energy can. So mass cannot pass the system, but energy can pass, right? That's control mass. How about control volume? Control volume, both mass and energy can across the boundary. So that's the major difference, right? I want you guys to keep this concept in mind. And now let's look at some examples. So for example, if you have a wind turbine, right, it will look something like that. You fix it on the ground, okay? And for a wind turbine, how does wind turbine works? So essentially, wind turbine would convert kinetic energy to mechanical energy, right? And when you draw boundary, you can draw different. Typically, you can draw any shape at any size. So let's say I'm just drawing a random line here, and to include both air and the turbine inside this region, right? So when you, my first question for you guys is, you can pause the video, think about it for a second. Is it control mass or control volume? If that's the case, right? So the answer is, you can think of, okay, here you go. When the air molecule comes in to get closer to the turbine, right? And also air molecule can also come out from boundary. So in this case, it should be control volume, right? And how about what if I change this boundary? If instead of drawing like on the outside, maybe I can just draw very close lines, or you can think as right on the edge of the turbine blades, right? If that's the case, I want you guys think about again, is it control mass or control volume, and why? Okay, here's the answer. Because air, since we draw a very close contour line on the turbine blades, right? The air molecule cannot penetrate into the turbine blades, right? So in that case, mass cannot go through, but energy can, right? So it will be control mass. It will be the final answer, right? Okay, let's look at another example. So what about human? If you have a person just standing there, and if I just draw a boundary like this, would that be control mass or control volume? How do you think about this question? Once again, we have to go back to the basic concept, right? Is there mass comes in or comes out? That's the determining factor for this question. So for a human being to survive, right, we need food, and also we need air. Okay, and then what comes out is kind of thinking about as waste, right? And also there will be energy flow out, right? Because our human body will radiate heat, right? So in this case, we know food and air has certain mass comes into the boundary, so we know it's definitely control volume, right? All right. The third example I want you guys to learn is, what if we have an AC unit, right? If you have to design AC unit to cool down the room, let's say you have an AC unit, and here's you, and there's a room, right? And you want to design how efficient the AC is, and how would you draw the boundary? Some of you guys may think about, okay, let's just draw a boundary around this person, right? And the next question is, would you consider this as control mass or control volume? Right. And the one important thing I want to point out for this specific example, in this case, we care about what? We care about the energy flows in, flows out, right? Because that's what the AC does, right? Trying to extract the energy from inside the room and dump to the environment, and so that's the way it cool down the room, right? Do we really care about food, air, or waste? Or when you design AC, do you have to care about how much the person have to drink water? No, you don't, right? So that's a very important concept for everybody. And as an engineer, you would need to make a certain simplifications throughout your entire career, right? So the more easier simplification or assumption you can make, you can make your problem easier and your life easier. So in that case, we prefer control mass, because we don't care about the mass comes in and out. We only care about the energy flows in and out, right? So we can cool down the human. All right? So in that case, it's control mass. All right, and we have talked a lot about the system, right? If we want to analyze system, we draw a boundary and we want to study what's inside, right? The system. What if there's something outside system? How do you describe it? So, not in the system. Oh, not in the system. We typically call it surroundings. Surrounding. Okay. So when you combine system plus surrounding, what do you get? What's the it's supposed to be everything, right? If you have defined something as a system, anything outside is your surrounding, right? So it can another one way to describe is universe, right? And the universe is a very special case. And think about this. There's what's the biggest boundary can you ever draw, right? Or define? It's the universe, right? And in that case, we don't have any surroundings. So your system is equal to the universe. And why do I say it's super unique? Because there's no mass or energy can cross the boundary, right? So when that happens, we typically call it, we have another name for it. It's called isolated. Yeah, isolated system is very ideal situation, very conceptual or theoretical. And typically when we can treat a certain system as isolated, and we can calculate based on like a certain type of approximation to get a reasonable number. Okay, so next I want you guys to learn is what is state and what is a property. So those two concepts are kind of really close with each other. That's why I want to introduce them right now. So let's look at state. What's the definition of state? So in thermal, a state represents where a system lies in thermodynamic space. Okay, I just use a term to explain another term, and you may wonder what do you mean by thermodynamic space? Thermodynamic space can be also defined as can be defined by using two properties. Why two, right? Think about it. If you have a 3D coordinates, right? In order to know where you are, you need X, Y, Z, right? To draw a pin or find a spot, right? How about 2D space? You need X, Y. You still need X, Y, right? So most of thermodynamic space we're dealing with is 2D, and that's why we need the two properties. And I know properties is a also very vague word. What do you mean by properties, right? What kind of properties do we have, or what kind of things we can call it as a property? So um, there there are many ways you can define properties, and one way to define is you can divide properties into intensive versus extensive. Right? What is difference between like between intensive and extensive properties? So it really depends on how much stuff do you have, right? And for example, if you have a system, you take a piece of it, that system, right? That small piece system has should have the same property with your original system. So if that's the case, we call it intensive properties. But if the piece of system and if you add if you take two pieces of system, right, and then or somehow adding them together, those small pieces together, if the properties start to changing, then we call it extensive system. Don't worry, we will look at one example, so you guys can better understand. So let's talk about what are the intensive systems. That's something that doesn't change. Uh, so can you get thinking about something? I know you guys probably have some answer. For example, temperature, right? Temperature. If you take if you take a maybe, let me use one example right now. Let's say you have a water tank, right? You're trying to take a cup of water, right? Assuming there's nothing lost, and the temperature of that one cup of water should be the same with the water tank temperature, right? So that's what I mean by intensive property. It doesn't change. So besides temperature, what else do we have? Probably pressure doesn't change too much, right? Or and also density, right? So those are very different, different unit, right? We can describe. How about extensive properties? How about math? Sometimes we just use a small m to represent the mass, right? Let's say instead of one cup of water, you have two cup of water, right? All of a sudden your mass has been doubled, right? It changes. So when that happens, the mass should be defined as extensive properties, right? What else? How about volume, right? When volume should be also double in that case when you change from one cup to two cups, right? And there's another special unit. You may never heard of it. It's called specific properties. So specific properties, and one of the most common one is called specific volume. Specific volume is volume divided by the mass, right? And what is the unit of this? We all know the unit for volume is meter cube, right? And the most common unit for mass is kilogram, right? So here we go. Specific volume unit is meter cube over kilogram, and you may this may look familiar with you guys, right? If you flip them, kilogram over meter cube, that's density, right? So one way to remember the unit for specific volume is you can always think about is 1 over density, right? And one thing I really want you guys to remember is what is the density of water. You should know this on top of your head. Is around 997 kilogram meter cube, right? Sometimes for simplicity, we just say 10 to the power 3, right? And how about specific volume in that case? How about specific volume for water, right? And it will be inverse, so negative 3, right? And don't forget to flip the unit, right? This is something you should always remember in the back of your head, okay? And of course, there are some books talk about there's some other type of specific properties, right? You have a specific internal energy, kinetic energy, or maybe a potential energy. We will talk about those things later on. And let's go back to the concept. We start talking about the properties, right? From here. And who came up with this idea? we need to know at least two properties to be able to find or to figure out or calculate any other type of properties. As one of the scientists you should know is James Maxwell. He's a great scientist. He contributed a great amount of knowledge to the science field for thermodynamics. Right, this concept seems very easy, but it has a very profound meaning. So let's look at one example. What do I mean by knowing two properties? We can figure out the specific state in thermodynamic space. So let's say we have a 2D coordinates, right? And one of the typical diagram you will see a lot is called PT diagram. P represents the pressure, T represents the temperature, right? So imagine we're trying to describe the state of this classroom, right? And you need to know two things. What is the typical room temperature? It should be somewhere around like 24 degrees Celsius, right? How about the pressure? Should be 1 atmosphere pressure, right? So if you know those two properties, you can draw a line, and the cross-section dot here is your state of this room, right? So
Okay, I found this on the web for.
typically that's the those two things, two properties you can describe like as thermodynamics in thermodynamic space. Okay, next we were talking about process. And go back to the this above example, right? We just described the room temperature pressure as this dot, right? And what if you are trying to cool down the room? How does the process look like, right, in thermodynamic space? Let's say we turn on the AC, right? When you turn on AC, the room temperature drop, right? Let's say we cool down to 20 degrees Celsius, right? And the room pressure doesn't really change, right? So we can draw another line, figure out a dot. So now we have two dots. Let's name it 1 and 2, right? So we're starting from dot 1 and end with 2. So if we draw a line between them, we also add arrow to indicate the direction of this process, right? So we can call this as a cooling process. Right? Process should be very straightforward, and it really describe how system moves in thermodynamic space. Right? And let's look at another example. Imagine you have a pump, and then we know how pump works, right? And the pump is typically dealing with a liquid. You pump water, right? And you kind of like pressurize the water into one direction. So, number one, the first thing you need to do, define the boundary. How would you define the boundary? You can just simply draw a line, like dash line, and saying, oh, this is your system, right? And the second thing is you need to define the process or state. What's the in this case? There's only two things going on, right? Water comes in and water comes out, right? You can. This is really important. You need to define state number one is what water comes in, right? And you can define state two as the direction of water comes out, right? And what if I ask you, if you draw this boundary box, right, like this boundary, Is it control mass or control volume? Because we have a water, right, comes in, and also pressurized water comes out, right? So we have a mass flow. If we have mass flow, then it means it's a control volume, right? Now, how does this process look like in the thermodynamic space? Let's draw another PV diagram. PT diagram. And our state number one, it can be maybe somewhere here, just a random dot. And because we pressurize the water, right, and we increase the pressure, typically the temperature might increase a little bit, but in this case, for simplicity, we just ignore it. So when you pressurize the water, which direction do you expect the second dot will be, right? Somewhere we should go up, straight up, right? Because there's no temperature increase. It may end up somewhere here. And we typically also draw arrow to indicate the direction of this process. All right. So that's a very simple example. So what if another concept I want to introduce is, so what do you have a bunch of this process, right? You may eventually make a cycle. So what is a cycle? Cycle is a collection of processes to the original state. So one example I will give you is, you may see this diagram a lot in the future. So something like this. So can you guys recognize what's the terminology, what's the name of this cycle? Right, some of you guys probably already know. It's called steam cycle. Oops. Steam cycle. And we're typically starting with a pump, right? This pump. And the second we go to boiler. And on the right hand side we have the turbine. And I will explain them one by one. And on the bottom we have condenser. So typically you go from state number 1 to state number 2. That's the one we just saw, right, above. So we indicate the direction, go up. And what kind of substance are we typically dealing with in terms of when we talk about pump? We're dealing with a liquid water, right? Liquid water. And after you pressurize the water, is still liquid, right? And then liquid water would go through the boiler. What does boiler do? Can you guys think about boiler? Boiler is you increase the temperature of water, right? And some of you guys probably may think about, what about pressure, right? Should the pressure also be increased? The answer is typically no, because when we convert water from liquid to vapor, and the vapor can expand, there's a lot of room for vapor to expand, so the pressure doesn't really increase in that case. So so here we can call it the state number 3, right? Because typically we have a vapor in this stage. Ideally, all the liquid has been converted into vapor. And then the vapor will go through the turbine, right? And the turbine's job is extract energy from the vapor. And after we went through the turbine, we'll have state number 4, right? The direction is like this. So now we just complete the direction of this steam cycle. Okay, now let's look at a little bit more in detail. So let's go back to the pump. Pump's job is pressurized liquid water and with a high pressure, right? The temperature doesn't really change. And then we pass on this pressurized water to the boiler. Boilers would typically rely on external heat sink or source and to heat up the liquid water and add more, provide more internal energy to the liquid water. By the way, all those liquid, there's some term called energy carried by the fluid, right? In this case, even though it's liquid water, it may carry a certain amount of internal energy, and the boiler's job is providing more energy to liquid water, so make the phase change from liquid to vapor, and then some molecules you may start to take off, right? By the way, here you might get a little bit confused. What is the difference between vapor and the gas? Oops, it's O here. Vapor versus gas. So major difference is vapor, all the molecules are not really too far away from each other, right? And for gas, you can think about all the water molecule or molecules are really far away from each other. And how do you bring, the next question you might think about, how do we bring those molecule distance of molecule close enough, right, to make it become liquid? Typically, you can reduce the temperature, right, make it condense, or increase the pressure. So that's the major difference between vapor and the gas. And now we just add a lot of in boiler we just add a lot of energy to the liquid water, make it phase change, and some of the molecules start to take off, right, and also carry certain amount of energy. And then we went through state number 3, and those like high energy molecules start heating the turbine blades, right? So you can think of turbine blades take the energy from the vapor, and once the vapor lose the energy or transfer the energy to the turbine blades, it will we will reduce, right? They'll change to a different state, and they will lose more energy. Once they lose the energy, some of them will start to condense, right? So at state number 4, we still have a vapor, but those vapors are low energy, or you can think of they lose a certain amount of energy. And in real life example, or a lot of cases, state number 4 is somewhere we call a mixture. So it has certain amount of liquid and also still have a certain amount of vapor, right? Because typically the efficiency, this conversion will never reach to 100%, right? 100% is a very ideal case. So after the turbine, the both temperature and the pressure will drop, right? Because we're trying to convert the energy to the turbine blade, and turbine can extract the energy to generate electricity and other stuff. So, and eventually, at state number 4, the condenser's job is trying to make sure all those vapor will be 100% converted into liquid water. And because typically when you have a pump, you don't want vapor go through a pump, it may cause some damage. So I just described the general process of this steam cycle. What does it look like in the thermodynamic space? Let's draw a diagram. Let's look at the PT diagram again. So we're starting at the number 1. You can just draw a random dot, start at a point, right? We have the liquid water at state number 1, and when we go, let's just think about from 1 to 2, right? We know the pressure increase, right? And we assume the temperature doesn't really change that much. So pressure increase, temperature didn't change. Okay, how about between 2 or 3? 2 or 3, we know the temperature boiler's job is adding a lot of internal energy to the liquid water, right? Make a change to from liquid to vapor. So the temperature change a lot, but we also assume the pressure is constant. It didn't really change. So you draw a straight line and indicate that's your state number 3. And next is we're going to look at the state from 3 to 4, right? We will the high energy molecules will go through turbine, right? And we will lose temperature, and all those molecules will lose their temperature and the pressure, right? So if that's the case, we will draw a line, like a curly line, to reach somewhere here, because both temperature and pressure drops, right? And by design, we want state number 4 has the same pressure with state number 1. So this dot will place somewhere over there. And then eventually condenser's job is reduce the temperature and bring back everything to the original state. And that's the direction of the flow. All right, next thing I want you guys to know is the equilibrium. Oops. Equilibrium. What does it mean? What does it mean for if something reached to equilibrium state? Right. So the definition is there's no gradient change in property. So that can also be think as there's no change in the system, or eventually it reached to a balanced or state or balanced condition, right? So I know it's a little bit conceptual. Let me give you one example. You would have better understanding. So let's say you have a chunk of steel, right? As a steel, it may be can be very hot, and you throw this into water, right? Into water, and eventually water, right? Eventually, if you come back like maybe 2 hours later, the steel will reach to the same temperature with the water. Or you can think about, you have a hot steel, throw in the cold water, or maybe water just in room temperature, or cold water throw in water. So eventually, when you come back after 2 hours, the state, the steel would have reached to the same temperature with the water, and that particular moment or state we call it equilibrium state. How did you draw this in the thermodynamic space? So let's say we y-axis represents temperature, x-axis represents time. So your initial there's an initial temperature for water. Let's say water is higher than the steel, right? You have a steel temperature, you have a water temperature here. So somewhere in the middle, that represents your equilibrium state, right? So because you dump the steel into water, so the there will be heat transfer between those two objects. Eventually, your steel will the temperature of steel will go up. The water temperature might drop. So eventually they reach to a certain point in time, and that particular moment is called equilibrium. State. Okay, so here's the difference. In thermodynamics, we care about the different state, like initial state or the final state, but we don't really care about what's happened in between them, right? The process, like how does a temperature change? What's the temperature gradient for either water or steel? How does it change with time? So if you're really interested with anything happen in between, right? You should later on you should take a heat transfer. And the heat transfer cares more about what exactly happened in between them. But in thermodynamic class, we care about beginning state and the end state, right? Anything just happen like you can think about everything just happen in split of second, okay? And also thermodynamics doesn't really tell you how this temperature varies or how does the energy transfer in between. You just need to know the general concept. So with that being said, all the system has the tendency to reach equilibrium. All system. Here I use the word try. Water doesn't really have a conscious, right? So it's just a metaphor. So all systems are trying to reach to equilibrium state. And later on, when we introduce the second law, thermodynamic, you will have a better idea why does it happen. It's not just happen to one particular object. Anything in the universe are trying to reach to equilibrium state. So another example you can think of, you may have a hot pizza, right? If you come back later, a few hours, the pizza will reach to the same temperature, reach to room temperature, right? And the pizza will become reach to equilibrium state. All right, and any object on Earth and will follow this law. And how about the things outside the Earth, right? Like how about our universe? And what what's the temperature in the universe or in the space? Is it should be equal to or we call T equals to 0 degree Kelvin, right? And that this expression should be approximate. Why is approximate? It's due to the quantum fluctuations, right? So eventually, everything in the universe will reach to the absolutely 0 degree, and so that's the tendency for any object in our universe, are eventually reach there. So, but as an engineer, right, when we create a system, we actually trying to push things away from equilibrium state. You can go back thinking about this steam engine example, right? Let's say you starting with the liquid water before the pump here, and you're trying to push it away, and by adding heat, right? When the liquid water goes through a boiler, and then eventually it will come back. You will see the process will naturally come back to reach to the equilibrium, or maybe like room temperature, room pressure for the liquid. So with that being said, last concept, something related to equilibrium is called quasi-equilibrium. What does quasi even mean? Quasi means it's a slow process to reach equilibrium. So quasi just essentially means a slow process. Why is so important for us, right? Why do we even care about like this quasi process? And because quasi equilibrium, oh, approximate approximation enable us to mathematically describe a process. Okay, and also second reason is quasi estimation, like approximation, also relate to the concept of reversibility, and that's a very important concept we are dealing with in the later chapters. Okay.